So now that we spent some time talking about water on land, we're going to now turn to discussing oceanography. And the first question to answer here is why does the Earth have oceans? And well, number one is that for whatever reason, and we're not quite sure where it all came from, but the Earth has a lot of water. Perhaps it came from the breakdown of minerals and other materials within the Earth. Perhaps it came from comets or asteroids or some combination of all three, but for whatever reason, the Earth has a lot of water. And the second reason is that we have certain areas of Earth that are oceans instead of one uniform blanket of water. Is the difference in density between the oceanic and the continental crust, as we discussed in the previous workshop. The oceanic crust is, of course, denser and rests lower on the Earth's surface. It's also thinner than the less dense, thicker continental crust, and this provides sort of a natural area for water to pool. This diagram on the right here, it's Earth's hypsometric curve, so it maps the distribution of different elevations across the Earth's surface, and you can see it's a bimodal distribution. So you have one peak for oceans and another peak for land, so that difference in level. The Earth has so much water that it actually does cover part of the continental crust, and has done so at many points in geologic history. This is the continental shelf, but for the most part, the water will pool above that oceanic crust. So the ocean is divided into many different layers and regions, depending on sort of the ocean depth in certain areas, as well as the presence of light. So, of course, we have most broadly our photic and aphotic zones, or sunlight zone, our twilight zone, and our midnight zone. And these are subdivided into the different regions. The abyss, which is most of the ocean floor, and the hadal zone, which is the ocean trenches, are two common ones that are mentioned. And we have some ocean temperatures here as well. And of course, we have the oceanic and neritic zone, oceanic being the open ocean, and neritic being sort of the littoral or continental shelf zone here. And the ocean bottom broadly is called the benthic zone. So things that are crawling around on the ocean floor, like lobsters and so on and so forth, are benthic organisms, whereas things swimming in the water column or floating in the water column, like fish or plankton, respectively, those are not benthic organisms. They're either planktonic organisms in the case of things that are floating, like plankton, or they're nekton organisms, like fish that can actually swim fast enough to move against the water current and aren't just drifting around. There's the term I was looking for. Pelagic zone is the broad term for things that are not benthic. Another good question about the ocean is, why is the ocean salty? And I recommend doing more reading on this, but in summary, what we talked about with rivers, we talked about that dissolved load. And, as water is flowing over the Earth's surface, it will, dissolve different ions. We see sodium, calcium, magnesium, and of course, chlorine. And these will be brought into the ocean. And over time, rivers themselves aren't that salty, they're fresh, but when water then evaporates from the ocean, of course, the salts stay there, and over geologic time, they've accumulated to the point where the ocean is salty. And some wonder, why isn't the ocean getting more salty? Well, part of it is because if a substance becomes too saturated, it will precipitate out. But there is also rainfall over the ocean and other effects that mean that some parts of the ocean are saltier than others. So we'll look at this map here and identify a few of them. So firstly, when we see areas with big rivers, so we see the Amazon a little bit here, the Ganges River, other rivers in sort of humid climates, we see these zones where the salinity is actually quite a bit lower. So we have a lot of fresh water flowing in all at once. Another area we see lower salinity is over the polar regions, especially the Arctic, where again you have a lot of snow melt and things like that, or in the case the Greenland ice sheet or the Antarctic ice sheet melting. Lastly, you see these regions of high salinity, sort of in the subtropical arid areas, and this is because there is a lot of evaporation, which is bringing out fresh water but not the salts, which locally increases the salinity. And if you have an enclosed basin like the Mediterranean or the Red Sea, those are sort of semi-enclosed, or the Dead Sea, which is fully enclosed, those salinity values can really rise. But if you have like the Black or the Caspian Sea, you have a lot of fresh water flowing into these. Relatively speaking, these aren't in as arid areas as the Mediterranean or the Red Sea, so the salinity isn't quite as high. So the water in the ocean, it moves, and it moves in a couple of different ways. And people talk about ocean currents, but there's two distinct types of ocean currents. There's deep currents and there's surface currents. Deep currents, they're often called thermohaline currents, and this is because they are driven by density differences that are a result of differences in temperature and salinity. So, for example, the Gulf Stream is enhanced by a thermohaline current that is moving warmer water up to the north. And eventually, once this water gets up to the north, it becomes colder, but it's saltier than the water that was in the north initially, so it'll sink and move back down and continue on the ocean conveyor belt. But the thing with thermohaline currents is, while they're definitely powerful and widespread, they generally move fairly slowly, and they can account for all the movement of water within the ocean, especially at the surface. And that's where we get into the surface currents, which are wind-driven currents. And you'll see some, like the Gulf Stream, have sort of this intersection between the deep thermohaline and the surface, but the surface currents are, they're faster, and they're driven by wind, and they're driven by this effect known as Ekman transport, where if you think of water in a number of layers, you'll see whatever direction the wind is going, the water will tend to move, depending on depth, in different directions relative to the wind. And this is due to the Coriolis effect. And the net effect of this is that the current will tend to move roughly perpendicular to the right of where the wind is going. And you can see that this creates a predictable pattern around the Earth, where anytime you get sort of these circulations of water, the warm current is always on the left, and the cold current is always on the right, or I should say, rather, the cold current is to the east, and the warm current is to the west. This is why East Coast, or the western part of circulations, have these warm currents, which can extend further over, of course, and then West Coast, like the California coast, or the coast of Western Australia, or the West African coast, they have cold currents. So you see that this pattern is present throughout all the big ocean circulations. And this is just a video from NASA showing wind-driven surface currents. And I just want to point out the difference here that, we look at, on a map, we see these straight lines representing currents, but these are only the net effect. This is what ocean currents actually look like. There's a lot of turbulence. They're sort of swirling around due to that Ekman transport. They're very dynamic features. We'll just zoom through a couple of different parts of this video here. Currents are very much net effects. Some currents are stronger than others. Those equatorial currents, I believe, tend to be fairly strong. But, this is what wind-driven ocean circulation looks like. So now we'll move beyond currents and talk a little bit about coastlines, and we'll talk about waves, ocean waves specifically. And ocean waves are quite different from, normal like physics waves in that they tend to move in this circular manner where the water particles in waves, they actually don't move. It's energy moving through. So when the wave goes by, the water particle will go up with the crest, if you follow my pointer, and then it will go down into the trough. So it'll perpetually move around and around and around. And this is the case until we get closer to the coastline, till about a depth of water, which is equivalent to half of the wavelength of the wave. So at this depth, the wave starts to feel the bottom, and this will cause the wave to increase in height or amplitude, and it will also cause the wave to start to collapse in on itself and form a breaker like this. And this is when you can actually get a little bit of net movement of water, but still the actual water molecules don't move too much except in this very small coastal section. It's just the energy moving through the water body as a whole. But we will talk about, before we move on to the next slide, we will talk about longshore drift later in this presentation, where you do actually get the net movement of water along a shoreline due to wind patterns, sort of more localized wind-driven circulation. So also going to talk about tides briefly, and we'll start off with this concept of the spring versus the neap tide. So not all tides are the same height, and this is because while tides are mainly caused by the moon, the sun also has a gravitational effect that also enhances the tides. So for spring tides, which occur roughly twice a month when the moon and the sun are in line, like in scenario A or B, you see that their gravitational effects are combined and you get the highest tide. In contrast, when they're sort of perpendicular, they're sort of working against each other, and the moon has a bigger influence on the tides than the sun. So like the tide will still be towards the moon, but the sun will counteract it a bit, so the tide won't be quite as high during the neap tide. So that is sort of the monthly sort of tidal pattern, but there's also, a daily tidal cycle to think of, where most places on Earth have semi-diurnal tides, which is 2 tides a day. And that's because if you look at the Earth again in this diagram, you'll notice that the water's higher not just on the side of Earth with the moon, but also on the opposite side as well. So as the Earth sort of rotates under sort of that gravitational bulge of water from the moon, it'll interact. There's 2 gravitational bulges, not one. So most parts of the Earth will experience 2 tides every lunar day. And a lunar day is 24 hours and 50 minutes long. And this the result of this is that the timing of the high tides will sort of shift throughout the month because the lunar day is slightly longer than the solar day we experience here on Earth. Now, some parts of the Earth, they have a diurnal tide for various reasons, usually due to sort of the layout of land masses. They'll only experience one significant high and low tide per day. And then other areas still, they'll experience two high and two low tides per day, but one will be stronger than the other. So that is it for our discussion on currents and waves and tides. And in this next part of the workshop, we're going to start talking about coastal geomorphology.